Hello, everybody. Thank you very much for inviting me to this great workshop. My name is Felix. I work at AI Sweden, and I'm going to talk about GPT-SW3, the first large language model for Swedish and the Nordic languages. So a brief outline of my talk. I'm going to very briefly talk about the background of this project, then go through some technical details regarding data, tokenization, training, evaluation, and scaling, and then conclude with some remarks about the release and an outlook. So GPT-SW3, as we call it, is the first large language model for Swedish and the Nordic languages. And by Nordic languages, I mean Danish, Norwegian, Icelandic, but we also trained on English and programming code. And the question is, why did we do that? Why a multilingual model? We are primarily interested, or were primarily interested in a model for Swedish, but we decided to go for a multilingual model for mainly two reasons. The first one is for languages like Swedish, rather small languages, it's very hard to get enough data to train a proper large language model. You see here in this table the number of native speakers for the Nordic countries and languages, and they're rather small. And the second reason is that the Nordic languages are typologically very similar. And I added an example sentence here in multiple languages. In English, it was a humid, gray summer day at the end of June. Just to give you an impression about the languages we're talking about, in Swedish, it's something like det var en fuktig grå sommardag I slutet av juni. So you see some similarities. Summer day, for instance, a sommardag. But if you compare Swedish, Danish, and Norwegian, you will see that there's a lot of similarity between these languages. They are almost the same, one could say. Icelandic is also related. I would say that half of the words are very similar, but the other half is very different. So Icelandic is a bit an outsider in our Nordic language group. So the timeline of this project was that we started it in late 2021. Half a year later, we had compiled a data set. Then we started training models, which was done in late 2022. After this, we trained instruction models, but the models have actually only been released very recently. And I'm showing you this timeline also because some of the stuff you will see in this presentation might seem a little bit outdated. And this is the explanation. It wasn't really outdated in 2022 when we trained the models. So regarding data, for the data, we used existing corpora. I'm going to show you which ones on the next slide, and also some open source data that we partly also scraped and gathered ourselves. And the existing corpora were mainly like the English data, and the open source data was mainly for the Nordic languages. And after data ingestion, we used several methods for data preprocessing. I'm only showing the most important ones here. So first, normalization with regard to white space and Unicode, then some quality filtering, followed by exact deduplication and fuzzy deduplication for each language separately. And you see that we, during the preprocessing steps, we started from roughly 1.5 terabyte of data and ended up with 1.2 terabyte curated data. And we call this data set the Nordic pile. And here is like a high-level overview over what we call categories of text data and the language distribution. So categories, the areas are, they correspond to the amount of data. We have a lot of web comment crawl, primarily in English. Then we have articles, conversational data that we partly scraped ourselves, especially for the Nordic languages. We have some books, Wikipedia, a math data set, and a significant amount of code, primarily Python and JavaScript. And regarding the languages, we basically got all the data we could, we gathered all the data that we could get our hands on for the Nordic languages. And we had, of course, not really a problem with English data. So the language distribution of the curated data set is shown on the right-hand side here. And we had mostly English data, followed by Swedish data, some Norwegian and Danish, and very little Icelandic, unfortunately. This was like the distribution in terms of categories and languages was not really what we wanted to train our model on. So what we did as a first step before model training was we weighted the data. So we did some up and down sampling while keeping the total amount of training data constant. We did some up and down sampling to obtain a target distribution, both in terms of categories and languages. So in order to achieve our target distributions, you see here in this table on the left-hand side, in the columns, the different languages, and the rows are the different categories, and we just upsampled or downsampled them in order to reach our target distribution. And what you can see is that English is heavily downsampled, with the exception of Wikipedia, and basically all other categories and languages are upsampled. And I'm not showing the target distribution in terms of categories, but in terms of languages, we ended up with this distribution on the right-hand side here. So mainly Swedish, 36%, followed by English, and then Norwegian and Danish. Unfortunately, still very little Icelandic, and some program code. So after we had like our data curated and reweighted, we did tokenization. And I'm going to go into a little bit more detail on this part. So why is the tokenizer important? What you want the tokenizer to do is break down your text into semantically useful subwords. So it shouldn't be, the text shouldn't be broken down too much on a character or near character level. What you want is like longer subwords that actually have a meaning and are quite frequent anyway. And one metric to measure the tokenizer performance is fertility. There are other metrics, but I'm going to focus on fertility here. Fertility is very simply defined as the number of tokens divided by the number of words. So for this example, hello world, which is maybe broken down into 4 tokens. We have 4 tokens, 2 words, so fertility is 2. And generally, lower fertility is better. Why is that? It has been shown by several papers that low fertility correlates with better model performance, specifically by Rust et al. For encoder models, BERT, and also recently by Ali et al., who have shown something similar for decoder large language models. With some constraints, this mainly only holds in a multilingual setting, it seems, and up to a certain vocabulary size. But here in this plot at the bottom, which is from Rust et al., you see that fertility, low fertility, I should say, correlates positively with model performance, just as the training data size does. So we're interested in a low fertility of our tokenizer. So what can we do to reach a good low fertility? We basically have 2 choices. First one is the training data that we choose to train, not the model, but the tokenizer. And what we did is we sampled a representative sample, 1% of the actual model training data, and we kept the language distribution and category distribution constant. That is a design choice, but we did this on purpose because it's conceptually clean, as there's no language or domain shift between the model training data and the tokenizer training data. But what this also means in practice is our tokenizer is a further prioritization of Swedish. We could have chosen, for instance, because Icelandic is already like poorly represented in the model training data, we could have chosen to, make at least the tokenizer fair in a sense. But we figured that the benefit for Icelandic would be very low and it would jeopardize our performance for Swedish and Norwegian. So yeah, we went with this variant instead. And the second step, or the second choice that you have that governs your tokenizer and its performance, is the vocabulary size. And here we applied several tokenizers with different vocabulary sizes on our data for the different languages and computed the fertility. So you see in this plot on the x-axis the vocabulary size and on the y-axis the fertility, and as a reminder, lower is better. And what we see here is that around, it's a matter of definition, but around 60,000, 64,000, the fertility seems to saturate or converge. So we chose 64,000 as a vocabulary size because what we see in this plot is that this leads to close to convergence fertility. And then going higher is actually not really useful because it leads to higher computational demand and so on and so forth. So we chose 64,000. And that was our tokenizer. We then evaluated and analyzed it. And these are on the left-hand side, you see the fertilities for the different languages. And what you see here, the first 4 data points are Swedish, English, Norwegian, and Danish. And the fertility is very similar for those 4 languages. It is slightly worse for Icelandic and significantly worse for code. And on the right-hand side, what we did here is we also trained monolingual tokenizers for each language with the same vocabulary and computed the vocabulary overlap. And there you see that the monolingual Swedish tokenizer has roughly 40,000 subwords that are the same, that are also part of the GPT-3 tokenizer. And interestingly, less for English and even more less for Icelandic and code. Interestingly, because the fertility score for English is the same as for Scandinavian languages. So our conclusion from this is that the tokenizer probably works equally well for Swedish, Danish, Norwegian, and English, and not so well for Icelandic and code. I'm saying probably because it's a bit more complicated, like there can be natural variations between the languages, so you can't really compare fertility across languages, strictly speaking. Yeah, then we applied the tokenizer. So our data set of 1.2 terabyte text was turned into 320 billion tokens. And that was roughly what we aimed at from the beginning, because that's the data set that GPT-3 used. And in terms of data composition, we had 78% unique data and 22 repeated data as a result of the upsampling I talked about. And this data composition is also very equivalent to GPT-3. Model training, this is the next step. I'm going to be very brief here because frankly, we followed standard practices and didn't deviate in any way. Oops. So we used the GPT-2 architecture with a sequence length or context window of 2048 tokens, which isn't much by nowadays standards, but it was like kind of standard in 2022. We used Nemo Megatron as a framework. Trained the models on Berzelius, which is Sweden's own supercomputer. And the learning rate schedule, you've probably also seen this before. It's a very short warm-up stage followed by cosine decay. And we chose the cosine cycle length equal to our dataset size, which is 320 billion tokens. So at 320 billion tokens, the learning rate has decayed to 1/10 of its maximum, which is reached at the beginning. We trained 6 models of different sizes. We started with 126 million and then scaled up to 40 billion in the end. And you see the hyperparameters in this table. They follow standard practices very well. And I should also mention that the 6.7 billion model is a bit of an exception in multiple ways. Different hyperparameters, also different data set composition. It's an exception. This plot shows the validation loss for our models. No big surprises here. The dotted line is the 320 billion tokens. And yeah, no real surprises here. We see a slight anomaly here at 320 billion tokens for the 20 billion parameter model. Like there's a little bump here, and I'm gonna come back to this when I talk about scaling later. So it's good to keep this in mind. Then we did instruction fine-tuning on top of the base models, the pre-trained models. And for this, we used a couple of publicly available instruction fine-tuning data sets, mostly in English, so 3 of them in English and 1 in Swedish. The English data sets we partly translated to Swedish, Danish, and also Norwegian and Icelandic, and then used all variants. And for the translation, we used our best base model, actually. The instruction fine-tuning itself, we used 2 formats for the queries and responses, and we did some stochastic merging of independent conversations. So it's not always, fine-tuning is not always done on one and the same conversation. It's sometimes also done on independent conversations that are concatenated. And the reasoning behind this is that we wanted to improve context switching capabilities. The learning rate schedule is kind of similar to what you've seen for the pre-training, with a few differences though. Evaluation. Unfortunately, benchmark for the Nordic languages is missing. Our Danish colleagues are working on this. They are working on something called scanned eval. So hopefully in the near future, we will have benchmarks for the Nordic languages. But for now, we can only do evaluation in terms of perplexity, so intrinsically in a multilingual setting, and we can of course use LM harness because our model was also trained on English. And I'm going to show you a few results. So first perplexity. Here you see Swedish, Danish, Norwegian, and English as the columns, and then we compare all our models against GPT-NEO-X20B and some Falcon models. And not really surprisingly, our GPT-3 model is better at all English than all the English models at Swedish, Danish, and Norwegian, and it is worse in English, but actually not too far away in terms of complexity from GPT-NEO-X if you compare it, 1.97 compared to 1.94. But I mean, that's certainly good that our model is better in perplexity for the Nordic languages. Then regarding LM harness, we evaluated our model and our model against GPT-NEO-X and GPT-3 on the task that you see in this table. And here we find that GPT-3 is generally the best on average, followed by our 40B model, which is better than GPT-NEO-X. But one also has to keep in mind here that we kind of compare apples and oranges because the model sizes of these three models are different. In particular, GPT-NEO-X is only a 20 billion model, whereas we're talking about our 40 billion model here. But that was certainly reassuring for us that our model in English, even though its primary target language wasn't English, performs rather well in English as well. So I'm going to compare our models on LM harness here. So what you see here on the x-axis is the model parameters in billion parameters and the LM harness mean score. And from this plot, what you see, the solid line, you see, not surprisingly, large models are better than small models. And the dashed line connects the two instruction models, so the 7 billion and the 20 billion instruction fine-tuned models. And here we see that the instruction fine-tuned models on average are better. Then we compare 0-shot to 5-shot. And here we see generally also that 5-shot, not surprisingly, is slightly better than 0-shot. There's one exception though, for the 40 billion model. Last technical thing I want to talk about is scaling. So what is shown here on the left is the loss function as it is used by the Chinchilla paper, Hoffman et al. They basically have this function to describe the loss as a function of the model size n and the dataset size d. But as you probably know, this requires the dataset size to be equal to the cosine cycle length that I showed before when I talked about the learning rate schedule. That is exactly the difference between Chinchilla and the Kaplan scaling paper. In our case, though, the cosine cycle length was always 320 billion tokens. So we can only analyze scaling for exactly this dataset size. So what I'm showing here is essentially I'm summarizing the terms E and B over d to the power of beta and call it E star. And then we have the loss only as a function of the model size for the dataset size of 320 billion tokens. And then we can use this formula and plot our loss against the model size. And that is shown on the right-hand side. So the black points are GPT-3. The 20 billion model is this empty circle here, and it is an anomaly. And that is because we had this anomaly in the validation loss, if you remember, that I showed earlier. So we actually, because of this, excluded it from the fit. So we fitted this function here to our data. I mean, it's only 4 data points and 3 fit parameters. You have to keep this in mind. But we then also compared it to the corresponding loss as a function of the model size that the Chinchilla paper presented. And what we find is that the parameter alpha is very close to the chinchilla paper. So of course we can't study the dependency on dataset size, but assuming that that's the same as for chinchilla as well, that would mean that also for GPT-3 we have this scaling behavior where if you have twice the compute, you should scale up model size and dataset size simultaneously and to the same extent. And then regarding the other two parameters, we have also E star. They are also in accordance between chinchilla and GPT-3, but the parameter A is very different. Okay, and finally, I'm going to talk about the release. The models were recently released. They're publicly available on Hugging Face. And as you can see here, we have both the pre-trained models, we have the instruction models, we also have quantized models. So feel free to try them out. We also have actually 3 papers about GPT-3. There's one paper that is the main paper, and then we have a separate paper about the dataset, the Nordic pile, and we have actually a separate tokenizer paper as well, where we go in depth regarding the tokenizer analysis that I showed you a little part of today at the presentation. I should also mention that those publicly available papers on the archive, they are from earlier this year and they're quite outdated by now. We have updated and extended and improved versions of all 3 papers that are submitted to journals, and one of them got accepted and will be published soon. The other ones are under review. Yes. As an outlook, our next steps, and we have actually already started working on this, is we want to do improvements with regard to GPT-3, and in particular, we want to evaluate it on the Nordic languages using the ScanDevel benchmark in the future. It's very important. And then also we started working on European models. We collaborate with different European partners in Germany, in the Netherlands, other Nordic countries. And in particular, we have one project called Trust LLM. And another direction that we're following now is we're training multimodal models. And yeah, I want to conclude by saying that we are very open to discussion, exchange of ideas, and collaboration. So if you have any ideas or questions or whatever, feel free to send me an email. Thank you very much.